All right, hello everybody. Welcome to EEE 135 Renewable Energy Systems, where today we're going to start chapter 6 called Charge Controllers and Inverters. So this is pretty much a power electronics section. But before we even get to that part, we need to talk about batteries because that's one of the main components of a charge controllers, right? Charge controllers are there to monitor the battery, to help make sure it can charge and discharge correctly and when to charge and discharge them. So before we even start controlling the battery, we have to understand what a battery is. Okay? So a battery is an energy storage device where it'll store electric energy to be used later. Okay? Now, batteries have charge and discharge cycles. So what happens when the battery is discharging? So this is the internal structure of a battery. Batteries have cell voltages. So a typical battery will have a chemical process within the battery to store electrons, right? This is different from a capacitor, where a capacitor just stores electrons purely based on a metal plate and just storing raw electrons. Here, electrons are stored in the chemical reactions that we can later undo the chemical reactions to release electrons. For example, lithium-ion batteries have the element lithium in it and some other things to make sure that we could swap the electrons between two molecules. Now, this is not a chemistry class, this is not a battery class, so we're not going to go into details, but notice like lead acid batteries there's chemicals and elements in there that will dissolve, will recombine, and then break apart the molecule structure, and electrons will come in and out of the valence shells. And that's how we store electricity or electric energy. It's good to note that for a battery, it is a chemical process that stores and releases electrons. Now, as an electrical engineer, all we really need to know is that it can hold voltage and have energy. So for us, a battery's internal components will have these metal plates that you put enough in parallel, you can get about 12 volts out of here, or 6 volts, depending what type of batteries you have. And there's going to be metal wires and lines within the battery to make sure all the electrons can come from the plates eventually to the battery terminal. So all the plates, the electrical wiring within the battery has an internal resistance R. So from our terminal standpoint, we have our outer voltage, and then inside a battery is you're going to have your internal voltage, but there's a resistor in between the two. That's impedance between the plate to the actual terminal itself. Okay, so when we want to discharge a battery, we're going to have energy built up within the plates, and we're going to push current out the battery, out the positive terminals. Now, just using Ohm's law, basic node analysis, if we're going to push current out the battery, the internal voltage, this OCV, must be higher than the external or the terminal voltage, right? Otherwise, current's not going to flow through a resistor. So current flows out the battery, we know that. Terminal voltage outside must be less than internal voltage because of the the voltage drop across a resistor, we call it delta V. Okay, so that's a big trick, is internal batteries. Typically, for a 12-volt terminal battery, the internal battery voltage might be like 12.6, 13 volts. So you make it like 1 volt or half a volt difference between these two, and that's how we could push the current out. Okay. Now, what happens when we want to charge a battery? Well, to charge a battery, we got to put current back into the battery. So current needs to flow into the positive terminal. And this time, we got to go through the resistor to the internal plates. So the internal battery voltage here needs to be kind of charged up. Now, this time, the current is flowing from the outside in, so we need to overcome the resistor. So it's kind of opposite from the previous one, is the terminal voltages need to be greater than the internal battery voltage to push current in. So this is why when you charge a battery, your voltage must be higher than the battery's internal voltage, otherwise you're not going to charge anything. Okay? When you're discharging a battery, your output voltage will be lower than your internal battery. So if you ever had to charge a car battery or something, you always wonder why. Why do we charge about 14.5 volts, but then the battery only pushes maybe 12.5 at a full charge? That 2-volt difference, that's the internal resistance that we're fighting between the charge and discharge cycles. Okay, this is very important because now we realize we need to accurately control the voltage to have a charge and discharge cycle, right? The battery itself is not smart enough to know which cycle it's on. We have to control the outside voltage to make sure we are charging or discharging, okay? Now, batteries can be very dangerous if they're used incorrectly. They can explode, overheat, lots of bad things can happen. So whenever you're charging a battery, you have to pay attention. You have to do it safely. There is a limit of current. There's only so much current you can push into the battery before it overheats. Now, let's think about it. Current will flow into the battery, charging the battery. When current flows through the internal impedance of the battery, there's going to be some heat dissipated. Remember, the power through a resistor is always I squared R. And then you can multiply power, multiply by time to get the total energy dissipated. So if you have a very high amount of current, I squared is going to be even higher. You can get a lot of quick energy buildup in the battery, and you might melt the battery, overheat. Okay? So there is always going to be a thermal limit of how much you could charge a battery. Now, how much current can you actually put? Well, you can actually do calculation. The current must be equal to the terminal voltage you apply minus the internal voltage of the battery divided by the resistance. Now, again, the terminal voltage is what we can control. So we can make a circuit with a control loop to real-time control the voltage and monitor the current to where we don't even need these two internal numbers. And that's typically how a battery charger works. A good battery charger will always monitor the current and slightly adjust the voltage, so we're getting the maximum amount of current through without damaging the battery. Okay? So precautions need to be taken when charging a battery. You have to limit the current so the battery because the battery temperature increases with current. We can't overheat the battery, right? A battery it builds up heat. A battery will naturally dissipate heat if the surrounding air is cooler. There's natural heat dissipation. If you really want, you could put like heat sinks on it, and you could put liquid cooling or something else. You really want to be fancy, but for the most part, you're just going to let the ambient air do its work. Obviously, in the winter, the battery can charge and discharge faster than in the summer because the temperature difference, you'll have more heat dissipation. Okay. Now, to limit the current, we have to limit the voltage, right? They're kind of tied together. Internal resistance is constant, so we must limit the voltage to limit the current to make sure we're underneath that damaging threshold. Okay. Now, when you buy a battery, there's probably going to be a sheet that will tell you this is a limit of current you could go through to charge as fast as possible. It might say, the limit of this charging battery is 100 amps at an ambient temperature of 80 degrees Fahrenheit, right? So as long as you're at 80 degrees Fahrenheit, you could charge consistently 100 amps. If you try to put 200 amps in, you're going to overheat it, and you do it too long, you're going to break it. Okay, so that's how you read this. So, what are the requirements to charge a battery safely? Well, number one, your charger must be DC output. Okay, if you put AC into a battery, there's going to be a positive cycle where you put energy in. There's going to be a negative cycle where you take energy out. You're not doing any actual net work. You're just wasting your time. So number one, you must charge with DC voltage to have permanent energy transfer. Number two, you need to have voltage control over the DC voltage so you can real time, like literally by not millisecond level, but maybe every 10 milliseconds or 100 milliseconds, you want to control that voltage. Okay. And it has to be very fine-tuned voltage control, not just plus or minus 1 volts. I want to have plus or minus 0.1 volt accuracy to that. Okay, so you need voltage control to then control the current. All right, current control. Remember, we got to have that because we got to limit the heat generated inside the battery. And number four, we have to have some monitoring system because we need to tell the microcontroller, what's happening. A feedback system is always needed to optimize any type of battery charger to minimize the charging time. Of course, you could not have it, but then you're going to charge at a very safe rate, which would be very slow. It might take you like 10 hours to charge a battery. But if you want to be fast, a good optimized system can charge a battery in like half an hour or 2 hours, at least to get a good percentage of it. Okay. So this is the requirements we're going to look at. we're going to start from the most basic all the way to the most advanced parts. Okay. So the very simplest possible charging is called a continuous trickle charger. Okay. We build a very simple circuit where we have a voltage source that's pretty constant. Current's going to flow out. There's a diode here to make sure we're not backfeeding the battery and it's not dissipating energy. So current's going to flow through this diode, and diode is a one-way check valve for current if you haven't done electronics. And we're going to charge a battery. Now, maybe we don't need to charge a battery anymore. So what we can do is we can have a shunt control. Shunt is a quick way to say parallel. And all this is a switch. So maybe the battery's kind of charged up or it's overheating a little bit because we charge it too much. We could close the switch and all the current will just flow through the shunt control back to the voltage source and nothing will go to the battery. Okay. Now, do we have actual voltage control here? No. This voltage source is set to maybe 13 volts, and that's about all we have. The best thing we have is we could short the voltage source away. So, do we have current control? Actually, we do, because the shunt will redirect the current away from the battery. So that is technically current control. So we do have it. We can divert portion of the current through a shunt and away from the battery. So maybe we could charge a battery for 10 seconds and it overheats, and then we'll shunt it for 5 seconds to let it cool down a little bit, and then we'll charge up for another 10 seconds. And we could just cycle back and forth between the shunting and the battery charging, right? And that's the most basic approach, right? So how can we control this device, right? So first you have monitoring, right? Somehow we need to have a voltmeter across the battery or a current meter in front of the battery. We need to check the battery voltage to know when to turn on and off the shunt control, right? We really should. Typically, this is used for very cheap applications, very small applications with internal batteries that you can't take out. So think of like really cheap kids' toys, like really cheap walkie-talkies. Maybe like a stuffed animal, a doll or something with an internal voice, or like a little paw you press to make a growling sound. Something like that where you just plug in a tiny little cable to charge it, right? That's all it is. Very cheap. No, this is definitely not used for solar applications, right? Now, we could get a little further out and have more control and get a better version of this, okay? Now, this is called a switched float charge controller. So it's piggybacking off the continuous trickle charger, except it's not going to be as continuous anymore. Okay. We're adding a voltage sensing circuit to then know when to turn on and off the switch accurately. Okay. In the previous one, we didn't really have anything automatic. So you either predetermined switching or you had to sit there and watch it. And yeah, it was very basic. Okay. Here, this is the new device we're putting in, right? And this is a microcontroller, right? It's going to have predetermined voltages we have to program. It's going to read it. A voltmeter reads it straight off the line. We're also going to have the regulator here to help have actual voltage control, right? So voltage control comes from the regulator to keep the voltage constant, and the switching on and off to turn on and off the entire circuit in regards to the battery. Okay, so we're adding more detail. Okay, so yeah, voltage control comes off the regulator, current control comes off this on-off switch to bypass any current flowing into the battery. Okay. What's good about the regulator is we do want to have constant voltage control, because as a battery starts filling up, the voltage inside the battery raises. So we need to raise our voltage in parallel with the battery voltage raising, right? So some type of power electronic device to help us would definitely go a long way in giving us smooth, clean voltage. Okay. So how do we monitor the system? Well, it's mainly this voltage sensing unit, right? This will literally control the switch to know when to turn it on and off to make sure that the battery doesn't get overheated. Okay. This is typically used for small devices such as portable LED lamps, camping gear, right? Self-contained units. right? You might use this as a for a car. If let's say you have a classic car or a sports car and you don't drive it too often, well, if you leave a car with a battery attached for like 3 months, you're going to drain the battery because all cars slowly drain the battery. So you might have a kind of topping off system where you could put a battery charger on your actual car and just leave it for 3 months. And that battery charger will just sit there and top it off over and over again, maybe once every 2 days or once a week when it needs a little bit of juice just to keep it topped off. Okay, that's kind of what this can be used for. Okay, we're not going to be cycling a lot of batteries through this. It's mainly just small, simple things. Now, what does a charging curve look like? Because remember, we're adding a microcontroller. It's our job to program the microcontroller. So what we can do is we could put upper limits of voltage and lower limits of voltage so that when we measure the voltage on the battery, if the voltage is below the lower limit, that's a signal we have to charge the battery because it's losing juice or it's losing energy. And we'll charge it until we hit an upper threshold. And this will signify that the battery is fully charged. If I try to charge it more than here, you might end up damaging it. Okay, so we could pre-program VREF2 and VREF1 based on the battery type we're using, and the manufacturer will typically give us a spec sheet. And then we could just let the switch charger go, and they'll have this charge. The switch will be off, so we could charge it. Then we could turn everything. We could disconnect the source, and then the battery will just go on its own. It'll, again, over a course of a week, we might lose some battery energy because it's attached to the car. So this white area, this non-charging, this could be a week. And then it could maybe take us 1 or 2 hours to top it back off, and then for a whole week, it'll be good until it loses this energy, right? So from an algorithm standpoint, when do we charge a battery? We could literally write an if statement in a microcontroller. If battery voltage that we measured is greater than the bottom VREF2, which is basically here and here, right? When the voltage gets below it, we immediately trigger the charging state and all your device goes into action. And will latch into charging state. It will stay online. So this is our lower threshold trigger. And it will stay in this charging state, and we can have a while loop while in charging state. If battery voltage gets above or greater than VREF1, the higher threshold, we will then exit loop, right? So that's kind of a just basic algorithm standpoint we could do. And this system will just run over and over and over again, right? Wait till voltage goes below VREF2, trigger charging, charge up until VREF voltage gets above VREF1 and shut off, and then rinse and repeat until we turn our battery charger off. Okay. So very basic battery charging curve, but it's effective. It does work. Okay. Now, we could get a lot more complicated and a lot more efficient than just turning it on and off every so often, right? Here, we can go to a 3-stage charger. And this is more what we use in today's world, is we use these 3- and 4-stage charging. Okay, so we'll typically, a fully controllable power electronic charger called a charge controller will follow these 3 states. The first state is called bulk stage, where we are charging the battery at the maximum current possible to get the fastest charge. Now, how can we maximize the charging in the bulk stage? Always charge at the maximum current possible. You see Imax right here? We will make sure that the current flowing into the battery is the maximum threshold that the manufacturer will let us. Now, a battery itself, when it's discharged, has a lower voltage inside the battery. A fully discharged battery for, let's say, a lead acid battery for your car will be about 10.5 volts. It's completely dead at 10.5. Okay. So let's say I have a 1 volt drop across the internal resistance. So if my battery is at 10.5 volts, I need to make sure my voltage of my charger is 11.5, right? And then that way we can maximize the current flowing through. To keep the current constant, I need to make sure my voltage follows the battery voltage. Because at 10.5, we're dead. But as we start putting 10% charge, 20% charge, our internal battery will creep up, the voltage inside the battery. So if it's at 10.5 now, our charger is 11.5. Well, let's say 10 minutes go by, and now the internal voltage is at 11, and we're still 11.5. We lost our max current. So as the voltage goes up half a volt, we need to go up half a volt. So we're going to move up with the battery voltage as it goes up. Okay, so that's why you see the voltage is constantly moving up. It's keeping up with the internal battery voltage raising up as it gets charged. Okay, so that's a constant control system where we need to monitor the voltage consistently, or actually we monitor the current. If we see the maximum current starting to dip, we could pop up the voltage to bring the maximum current back up a little bit. So just to make sure that main current, it might be wavering up and down, but we need to make sure it's as constant as possible. Okay. So main takeaway here, bulk charging stage, make the current constant, and the voltage will be dynamic, always following the battery voltage until we get to the upper threshold. Okay. About right here, the end of the bulk stage, we can get to about 80% charge. So 0% to 80% charge, that's a bulk constant current charging. This is why if you ever went to AutoZone with a dead car battery, they could always say, hey, I'll give you a quick charge in half an hour, but if you want to get fully charged, you got to keep it overnight. Okay, the battery, it's always the easiest to charge between 0 and 80%. The last 80, 90, and 100%, that's always going to be longer, a lot harder and longer to do than the first 0 to 80%. You probably notice it with your cell phone as well. If you plug it in, going from, let's say, 20% to 80% is pretty quick, but it'll take a lot longer if you want to top it off to 100, right? It's not linear across the whole thing, right? You know, if, for example, you got like an airport, you want to go in an airplane, it's like, oh, I want to make sure I'm at 50%. It'll charge from 50 to 80 pretty darn quick. But then that last 80, 90, or 90 to 100, you're like sitting there waiting. Why is it taking so long? It's just because that's how natural batteries work. The last 10% is always the hardest. Okay. So, but we want it. So what's the second stage? To go from 80% to 100% is called the absorption phase or the topping phase. We'll put in the last little bit of energy into the battery. So how do we maximize charging the absorption phase? Well, number one, we hit the maximum voltage we possibly can. Any more voltage that we put on the battery will probably destroy it. So we're at the maximum voltage. So we're going to stay constant voltage. And as internal battery voltage gets higher and higher and higher, the current will decrease, right? So at the beginning of the absorption phase, where you still have pretty high current, but towards that last 95, 97%, our current's going to be pretty tiny. It's going to take a lot longer, okay? So how do we maximize charging in the absorption phase? Just make sure we have maximum voltage and just hold it constant. The current's going to ramp down naturally because cell voltage increases. We can't do anything about it. That's just the tax we have to pay. Okay, we can get from 80 to 100% charge on this. It does take much longer. It might take overnight for a car battery, to give you an idea. Okay, so that's your second stage. At this point, we're 100% charged, but we want to make sure that the battery stays charged forever. So we go into the third stage called a float stage. This is where we'll continuously monitor the voltage, and if it gets below that VREF2, then we're going to pop off a little bit of current and raise our voltage a little bit just to make sure that we keep it topped off. So if you see, this is like that charge, discharge state. It's the same thing as a switch float charger we did before. Okay, it's literally the switch float charger at the end. Okay, so how do we maximize the charging in the float charge stage? When the battery is self-charged or discharged, the battery voltage lowers a little bit, we could turn on our trickle charging mechanism and just pop in a little bit of current, just go from that 97% back to 100%, right? Basically, keeps the battery topped out at 100% charge at all times, right? Obviously, in a car battery, you're not going to do this because you typically disconnect the charger, put the car battery back in the car. But for a stationary system like your solar PV system with batteries, this will be a constant thing happening all the time if you're not using your battery for your own house, okay? So 3 stages, right? Constant current, bulk, constant current, absorption, topping off, and then the float trickle charging, okay? Now, how do we control this system? We know the 3 stages we need. So this is our battery. We have a current sensing amp meter basically to sense a minimum current. We have a voltage regulator to change the voltage that we need, and then we have a feedback controller. Okay, so in this is a feedback loop. What is the device to input into the control system? What device gives us information to then act? What's this current sensor? We're always going to track the current to make sure we're either at that maximum current or that we're at that slow ramp down on the absorption phase. Okay, we're continuously sending current information back. The feedback controller will then make a decision to change the voltage as needed. So in the constant current state of the bulk stage, if we see the current dip, we're going to pop up the voltage a little bit with the regulator. The feedback will literally say, hey, move up 0.1 volts. And then let's check the current again. And it's just going to be a continuous feedback system to make sure the battery is fully charged. Okay. Which device is the output of the control system? The voltage regulator. Okay. So current senses, feedback controller thinks, voltage regulator does. And that's your standard control loop. Okay. Now, we could go even more complicated. Well, we know we have a three-stage system. We know the basic feedback system. We can now add in a pulse width modulation charging system or a charge controller. Okay. Now remember, DC solar panels inherently don't have any on-off switch. A DC solar panel, it basically the sun shining, is pushing current through with a voltage. Now we can put a switch in front of it called a voltage regulator to turn it on and off. Now the question is how do you control the voltage, right? Well, if I want to go from 10 volts to 5 volts, what can I do? Well, one person would say, well, let's just put 2 resistors and do voltage divider. Technically, if you do that, that's an incredible waste of energy. 50% of your energy can get thrown away because you're doing resistor division. That's a terrible idea. We don't use voltage dividers with resistors to lower voltage in today's world. Instead, we could literally switch the solar panels off and get 0 volts. And then if 50% of the time we're at 10 volts and 50% of the time we're at 0 volts, if we average that time out, it'll be a net 5 volts, right? And that's exactly what pulse width modulation does. Is it can do a voltage control by turning it, literally physically turning it on and off the voltage input. Okay, so yeah, let's read it here. It says DC solar panels do not have any inherent voltage control, so you only have 2 options, on or off. The controller can control the width of the on pulse. So right here, let's say we want a lot of voltage to start charging the battery. Okay, see the battery voltage is kind of low. We'll turn the switch on and we'll have a wide pulse to where we're charging the battery. But maybe right here, the battery's a little overheated. Let's disconnect it for a little bit, right? And then we'll charge it back on and disconnect it and charge it back on and disconnect it and so on, right? So as time goes on, notice that we'll eventually have more off time than on time because the battery can't take that much energy, right? If you can't push a bunch of current at the very top of when the battery's 95% charged, it will burn itself. Okay. So the whole point of pulse width modulation is you could shorten or widen the voltage pulses used to charge a battery. Now, the one thing a pulse width modulation controller can't do is it cannot lower or increase the voltage of the height of the pulse. The height of the pulse is constant, but by having this dead space in between, we could lower the average voltage at the end of the day. And that's literally the whole idea of pulse width modulation. Okay. So it's literally just an on-off switch. That's all it is. But it's a very controllable one, and we're very smart in when we turn it on and off to get a overall voltage that we can control. Okay. So how does it look like within a circuit? Pulse width modulation, or we call PWM controllers, will pulse the voltage from the PV panel on and off. And why do we do this? It's because we want to match the maximum charging current limit. Okay, if you remember, we go back over here, right? You see how you have your current right here? We want that constant, but you see how your voltage increases? Okay, we're going to have the maximum voltage, but we're going to pulse width modulate, we're going to chop it up to where the average is going to be down here. So down here, we're actually going to have a little bit of width, and we're going to get bigger and bigger and bigger as we go up here. And then we're going to go back down on the float stage. So that's a pulse width moving up and down. You can kind of see here we got pulses on and off, and our current can keep going up or the voltage of the battery can keep going up as we charge it up. Okay, but the whole idea of pulse width modulation, at the end of the day, is we want to maximize the charging current, but we want to limit that current to what the battery can hold before it blows up. Okay, so it's a very fine line we're toting of being efficient with our time and not damaging the battery. Okay, when the pulse is active, we charge up the battery and we it heats up. When the pulse stops, we stop charging the battery cools down, and this on and off cycle will keep the battery happy. Okay. Now, this is not a power electronics device, so we're not going to talk about. We might talk very little about the pulses, but not too much. Right? There's a whole. You could take your entire career being a power electronics engineer and talk about microcontrollers and pulse width modulation of a bunch of different devices. It's not just battery chargers. PWMs are pretty much everywhere in the world right now. It's the most effective way to get energy while changing the voltage to whatever we need. Okay. Now, there are some very fancy chargers in today's world, they're typically like $1,000 or more, that have a fourth optional stage called equalization stage. Okay? Now, when you have lead acid batteries in general have a life cycle, right? You ever notice your car battery never lasts past 5 years, or your cell phone never lasts past 4 or 5, right? Batteries don't last 50 years. And that's because the chemical process within a battery deteriorates the material inside it. A lead acid battery is acidic by nature. The acid will start melting the plates and doing a lot of bad chemical reactions to where just eventually the battery dies. Now, we could prolong that death by cleaning the battery every so often. And that's what the equalization phase does. Okay, so the purpose of the equalization phase is we can actually put a higher than normal voltage, it's called an overvoltage, is applied to a battery for a long time, like let's say a couple of hours. So whatever our safe battery voltage is, we're going to add it plus 1 volt to that. So if it's maybe 13.5, we're going to go 14.5. And we're going to keep it on for a few hours. Okay. And what ends up happening is this extra voltage. So what does the stage actually do? Set your voltage 1 higher than the flow charge voltage. It'll induce gases on the plate. So literally the metal plate, it's within a bunch of liquid acid. The higher voltage will start messing with the plate and the chemicals on the surface, and you'll kind of boil the acid around you. So you're literally creating bubbles on the plates. And what ends up happening is the bubbles you create is going to knock off all the gunk and the extra buildup on the metal plate. So the metal plate left alone, there's going to be like, not rust, but not even oxidation. You're going to have a chemical reaction with the metal plate. You're going to get a bunch of extra gunk, right? And goo on it. Anytime you have gunk on the plate and you're not touching the acid, you're losing battery storage. So by putting those forcing the bubbles on the plate, it'll naturally knock off the gunk and it'll fall to the bottom of the battery. Okay. So and you typically want to do this maybe like once a week, just to knock off that extra gunk on the battery plates and keep them as clean as possible. It'll never be 100% perfect, but that gunk on the plate builds up over years, and the more times you can knock it off, the slower to build up, the longer your batteries will last. So in essence, when you have an equalization stage, your battery, instead of lasting 5 years, might last 8 years. So you get extra 3 years out of it. So, and this is a good thing. So if you ever have a chance, you definitely should get equalization phase stage on a battery charger, and it's called a 4-stage charger instead. Okay. So that's pretty much what we currently have. The best, greatest technology is a 4-stage PWM charge controller. They're probably a couple $1,000 if you want to do your solar panel installations, but it's the best of the best, and I wouldn't get anything less. Okay. Now, we talked all about what's happening, how the algorithms needed for a charge controller, just kind of a light overview. Let's do a little bit of design work. Okay. Now, as a renewable energy engineer, I'm not going to say you have to understand what happens inside a charge controller. It's nice to know. That's what I'm telling you. But I'm not going to say you have to get a microcontroller from the shelf and build it. That's the power electronics engineer's job. But you need to know how to get the correct charge controller. There's a bunch of different ones at different current levels, voltage levels. Your job is to take all the pieces to make a combined system. That's what a renewable energy engineer does. So you need to specify, for example, size and charge control. You need to specify what's the current limit for a PWM charge controller that you buy from manufacturers. And there's some guidelines involved. It's not just, if it's 100 amps, get a 100 amp charger. Number one, especially for these battery systems, you want to add a 125% margin error. So we want to have a derating factor at 25%. Okay, derating factor just means if we need 100 amps for a battery, we need to make sure charge control is more than that by 25%. Okay, that's what it means. We need to give us extra room in case something crazy happens. We never know. Now, that's just a good rule of thumb, give a margin error. And then the NEC, National Electric Code, requires that any system with 3+ hours of continuous operation, meaning that battery is continuously discharging for 3 hours, must include a second 25% derating factor for the rated current to account for the constant heat buildup in the wires. So if your solar panel system or your solar array system has a battery system in your garage, and you expect the battery system to run your AC and all your power, your electronics at night for more than 3 hours, which is probably so, you need to add a 25% extra derating factor. And they're multiplicative, so it's not additive. Okay. So for example, let's assume you have a charge controller you bought with 100 amps rating. Now you think, well, I bought a charge controller for 100 amps. I can match a 100 amp solar array system, I'll be done. No, that's incorrect. And you're probably going to end up breaking their charge controller. So we have to kind of go work backwards. How much current can the solar array push through a charger, a 100 amp charge controller safely? So we're kind of doing a little backwards engineering. 100 amps the end goal, we must work backwards. So we know a margin error is 125%, right? So if we have 100 amps, our original current coming in must be I times 125% equal 100 amps. So if we reverse calculate this, we can only push 80 amps through the charge controller, taking into account the margin error we want. We're going to go second level with the NEC requirement, because we're assuming this is for solar installation with continuous operation. We need to take 80 amps and say, well, what's my current before the extra derating factor? So we're going to have a second one of I times 125% equals 80 amps. And this is going to be 64 amps, right? So this is a true solar array limit, is we can only get a 64 amp system attached to a 100 amp charge controller, right? Unfortunately, I really wish this 64 amps number would equal this 100 amps number on the charge controller sheet, but the charge control people don't want to do that because the 100 amps looks better than 64. They don't want to make more money, so they sell it at 100, and it's your job to do the number crunching, right? That's just how business is. You're just going to deal with it. Okay. But in the end of the day, that's why you have a job, right? You're the person finding those rules in between. And then you're like the middle person taking a solar array company and a charge controller company, and you're mashing it all together and kind of knowing these small little nuances of this needs to match that with a 125% rating. That's what your job and that's what your expertise will come into, right? Again, go look at Solar DIY Reddit. It's hilarious that people don't know any of these rules. They're just doing whatever, and then come back in 3 months complain that their system broke. And like, that's because you're not an engineer. You have no clue what the hell's going on, right? Leave it to professionals. That's what we really should do, but people are cheap. They don't want to. All right. So let's take our 15-minute break here. Exercise number 1. I want you to size the charge controller on your own. We installed, so it's already done, a solar array consisting of 6 40-volt 250 watt modules, all of them in parallel. The short circuit current is rated for 5 amps. And then I want you to size the charge controller with rated voltage, current, and power. So each module is 40 volts, 215 watts, and 5.8 amps. And you have 6 of these in parallel. Right? So I'll let you do the number crunching and some basic circuit analysis. We'll come back in a 15 minutes and check in, see how you did. Okay, so see you in a little bit. All right, hello everybody. Welcome back to EEE 135, where we're talking about Chapter 6 charge controls, coming back from the exercise we just talked about. And this is sizing a charge controller. So let's go ahead and see how we do this. So remember, we talked about we had 6 solar arrays, solar modules in parallel of 40 volts at 250 watts. Each module short circuit current is rated at 5.8 amps. So you always want to take the worst case current, which is short circuit current, to figure out your total. So they're all in parallel, meaning all 6 of them you need to multiply by 5.8 amps because current in parallel always gets added up. So there's 34.8 amps total current coming out of the solar array setup, right? So for the constant current coming out, we're going to have 125% added to the short circuit current or multiply into a short circuit current for the margin of error. We're also going to multiply another 125% because this is for a solar array. So you expect these batteries to be used for more than 3 hours consistently. And then you multiply by 34.1 amps. So your net total is 54.5 amps. Okay, so that's how much current we need to, that's the current size we need for a charge controller. For the power itself, or the 6 modules, each one is 215 watts. So you just take 6 times 215. So you get 1.29 kW. That's another spec we could carry over. The voltage for the charge controller is, well, they're all in parallel, so the voltage isn't changing. So it's just 40 volts. So the charge controller spec overall, you're going to need a minimum of 40 volts at 55 amps with a total output of at least 1,300 watts. So these are minimums. Obviously, you can go over these, don't go under them, and just after that, choose the cheapest one that fits your system. Okay. So that's just a quick example and of showing the calculations needed. So we kind of went over the battery charging side. Now let's start talking about the solar panel side. Because remember, a charge controller is connected to the solar panel for the source, and the battery is the load. That's how you imagine a charge controller. So the charge controller not only has to control the battery charging, it also needs to control the solar panel as well. Right? Remember, we talked about maximum power point tracking. So just as a refresh, MPPT is you want to choose to correct the best voltage and current operating points to maximize the power output. At the end of the day, more power means we're charging the battery faster, we're powering more devices, we're saving money. Okay, so this is kind of graph. If you remember, there's a certain operating point where you get your IMPP, VMPP, I times V is multiplied, and then your power gets a kind of an upper crest. So we're going to say it's about right here. Right? So to efficiently charge a battery and operate your DC system, we should always strive our hardest to operate at this maximum power point. And the charge controller is now the object that will make sure we stay at that point. Okay? Now remember, maximum power point tracking can have variance, right? So sunlight intensity, meaning how bright the sun shines, which could be altered by the clouds, time of day, in the morning and nighttime, it doesn't shine as brightly as in the noon. Temperature has a small play in it as well. All these, if you remember, will change where your maximum power point lies. And this can change hourly, daily, even by minutes. Okay. So for varying radiances, notice that the overall current gets lower. As the low current gets lower, your maximum power point for your power goes down. Varying temperature changes your voltage, your maximum power point voltage, which will obviously change your active power outputs. So we need to always check the voltage, always look at the current, find out where those 2 points are, and make sure that our charge controller is pulling current and voltage at that exact point. Okay. If the maximum power point changes randomly during the day, again, clouds could come over for that day, how can charge control keep track of it, right? So this is not a it's not a pre-programmed system you walk away from. You must continuously monitor for a drop in power output and readjust to the new maximum power point. So this is a continual observation where you're going to run a control loop over and over and over again just to make sure you're at the operating point, maximum point. You don't have to technically, but then you're going to have a subpar system. So any charge controller that is of good quality will have some type of algorithm to do this. It's called maximum power point tracking. It should be like a feature you see on the spec sheet. Now, how are we actually going to do that? This is where we're going to start putting our programming ideas together. Well, one way we could do that is just the trial and error, right? So we can always start at a lower voltage point and then take a measurement of the power and compare it to our previous point. So we'll start at a low voltage and we'll keep creeping up incrementally and we'll check the power. If the new voltage point has a higher power than the previous one, well, let's use the new one. The previous one's not good anymore. We could keep on doing this until we eventually get to that peak. So for example, here we try V1. For V1 is this low voltage. So we have high current but low voltage. So we multiply our power, it's going to be down here. Well, is that the best? We don't know yet, because remember, the charge controller does not have this graph. This graph is just for us to, as a result, for us to analyze what's going on. But realistically, the charge controller does not have this map. It's blind. So then its next option is, let's raise it by 0.1 volts. So maybe instead of 0.6, we go to 0.7, right? And we'll try this voltage. So voltage 2 will then measure a power of, which is higher than P1 right here. Well, then that's obviously a better place. So let's throw away V1 and let's operate a V2. But can we do better? Yeah, why not? So let's try V3. We're going to try V3, you get P3. That's better. We're going to try V4. V4 is better. We're going to try this middle one right here, MPP, and that's better than P4 slightly, but it's still better. We should use it. Now, question is, how do we know when to stop? Well, let's try V5. Well, V5 we can try, but notice P5 is less than the maximum power point. So boom, we already know we reached the max. We went over that hill and now we're going back downhill. So once we hit V5, I know that it's worse off afterwards. So we stop and then we back rank it. We go back one voltage level to V4, and that's our new maximum power point. And we're going to stay here until we see a drop in power. Once we see the NPP drop, then we'll start our process all over again. Okay, so we start at low voltage, measure the power, compare it to the previous point, keep increasing voltage until we see a decline in power, go back one voltage step and hold. This type of algorithm is called the perturb and observe algorithm. So you have a system, you're modifying a little bit, you're increasing it just at maybe 1 or 2% and observing what's happening, and we're just going to incrementally, safely crank up to a better power rating until we hit the maximum. Okay, so this is basically a giant while loop that consistently happens with an if statement attached to it, and you're just going to run this in your microcontroller over and over again until you get to the maximum point. Once you get to the maximum point, you want to have a break in the while loop, so have an exit command, and then hold that in the memory, and we'll stay there. We'll also probably have a second if statement outside, a nested second loop, while loop out of it, while that will continuously monitor the power. And if we see a decline from the maximum power point, we'll then execute the inner loop. And it's just a system that should be running 24 hours. Okay. Now we don't want to sit here and change the voltage over and over and again. Once we find the voltage, we stop. So the inner loop of testing voltage should only happen when we have a change, but it should be a continual hour loop of observation at all times in case the clouds come over and the maximum power point changes or something like this. Okay. Yeah. So this is kind of a block diagram to show you the inner work, the logic. So you start, set module output voltage relatively low, measure volt and current, calculate power, right? Is power greater than the previous iteration? If this is the very first step, the previous iteration power is 0, right? If it's yes, then we increment our output voltage to a little bit more. So we'll go to V2, which is maybe 0.1 volts higher. And this loop will continue over and over and over again until this if statement is false. Once this if statement is false, we know we have that highest power, and we'll hold the module between the current volts and we'll actually go back to the previous voltage, Vn minus 1, and that will be the ideal situation. Okay? So it's just a block diagram of the loop system. But definitely, anytime you have a information loops back like this is a while loop for sure. Okay. So how does the circuit-wise look like? So the MPPT charging controller circuit is, you'll have a solar panel that has its own maximum power point. You need to figure it out. You're going to have a DC to AC converter right here. So you're going to take your DC voltage, convert it to AC. While you're doing that, the maximum power point control microprocessor, this is a centralized controller, it's going to get your output voltage. It's also going to get the current, the power, and then it's going to go and change this DC to AC converter, because this converter can control the input voltage right here, and thus the voltage of the solar panel itself. Once that's done, you have an AC output. You're going to have a transformer to probably increase the voltage to 120 volts or some higher level is more efficient. We're going to convert it back to DC, and then we're going to charge a battery. So it's kind of, if you draw a line down the middle, there's two distinct stages of a charge controller. You get your input side, which controls a solar panel, and then your output side, which controls a battery. Okay, and the middle link is the AC link right here. So which part controls the maximum power point tracking of the solar panel? It's a maximum power point control processor and the DC to AC converter. These two are the control loops for controlling the solar panel. Which part controls the 4-stage battery charging cycles? This will be the maximum power point control microprocessor and the AC to DC converter with this PWM switch and regulator. It's kind of all grouped together like this. Now, question you always have is, why do we convert DC to AC and AC back to DC? Doesn't that sound like a wasted link? Right? One of the main reasons we want this is we want to completely separate the DC voltage between these two systems, right? So that this DC solar voltage can be any rating independent of the battery voltage. Because maybe later you want to increase the battery voltage. If you want to increase the battery voltage, you don't want to have to increase the power, the solar panel capacity as well. They need to be independent, so we can't have a direct DC link between these two when you convert it, and it's easier to do it, have a transformer in the middle to help step up and down the voltage. So it's just there to segregate the two systems, that there's no overlap. Okay. So kind of, if you want to look at the spec sheet and start figuring out what type of charge controller you want, these are the type of things you need to look for. You need to obviously find your output current, how much current is going to go to the battery, the maximum solar array size it can handle before it stops working, the nominal voltage for the battery, your open circuit voltage for the solar panel. So basically, this is your input voltage from the solar panel, normal battery voltage is your output to the battery. Standby power consumption. So let's say nothing's happening, the battery's fully charged. What is a parasitic loss of the just keeping everything online? It should be very low, like maybe 1 or less than 1% of the total power. But anytime you keep a controller on, there's always a very small amount of power you use just to keep circuits running. Just monitoring the system as a whole takes power. Okay, charging regulation. So how fast, how much can you charge a battery? Voltage regulation set points. What's that positive VREF? The VREF 1, VREF 2. What's the range of voltage it can charge on a battery? Remember the equalization voltage. How much voltage can it put extra into the battery to burn all the gunk off the metal plates inside the battery, right? Battery temperature compensation. So if the battery gets hotter than it normally is a charge control smart enough to readjust all your settings? So for example, if it's 110 degrees outside, the battery is naturally going to be hotter versus when it's 60 degrees outside. Is your charge control smart enough to sense a temperature difference and adjust its voltage profile based on that temperature rating difference, which obviously affects the battery? Lastly, you have a power conversion efficiency. At the end of the day, you're taking power from the solar panel, you're putting it into the battery. It's never going to be a one-for-one conversion. There's always losses anytime you go into the device. What's the power loss, right? 3% is okay. 1% is great. Anything 5% is not commercially viable. That's just a waste of money. Okay. So I'll be looking somewhere. I'll be happy if it was 1% or less, but I'll probably tolerate up to 3% power loss upon delivery. Okay. If your charge control does not meet your system spec, so some of these specs is not, the charge controller that is offered to you does not meet what you have installed or designed, what can you do? You can't ignore it, right? You need to either downsize the solar array or battery. So if you have the voltage or the power rating and current ratings to it, you got to modify your battery design, modify your solar design, or solar array design, one of those two. Or you need to go buy another charge controller, one of those two things. Now, ideally, all this should be pre-planned to where you're not going to make a mistake at the very end and order the wrong thing. It should all be seen far ahead in advance in the design phase. Okay. Now, let's kind of look at an actual charge controller spec sheet and see where those numbers come in. So for example, you have nominal battery voltage. This one, it auto senses voltages somewhere between 12 all the way to 60 volts DC. So you could have a number of battery banks in any of these increments, and it'll register it and then pre-program itself to then run at that voltage level. Okay. But you can't do like, it's not 12 to 24. So you can't put like 13 and a half. It's either 12 or 24 or 32 or 36 or 48. Okay. Output current 60 amps maximum is the limit it can push out to the batteries. So when you're building your battery banks, don't expect it to push out more than 60 amps. So if you have a huge battery system, your charge controller might not be able to put enough current to charge it in an acceptable amount of time. So there's always a sizing of battery bank to charge controller. Okay, maximum solar array size. This is on the input size. For a 12 volts DC solar system, you can only do 800 watts. All the way to a 48 volt system, you can handle up to 3200 watts. Higher voltage, the less the current for the same power. So naturally, when you get higher voltage, keeping the current the same, you can always push more power out. Okay. This is your open circuit voltage for the highest level, right? Standby power consumption less than 1 watt. That's pretty much nothing. There's your charging regulation. This actually has 5 stages. So bulk, absorption, float, silent, and equalization. Right? And there's your voltage regulation set points. 10 to 1280 volts, user adjustable, so you can literally set that VREF1 and VREF2 as you wish. Here's your equalization voltage. This one can do up to 5 volts above the set point. It automatically terminates when completed, so it's an automated system. You don't have to go manually turn it off. Battery temperature, you could, as long as you put a temperature sensor, it could automatically sense temperature and adjust all of its tables. Let's kind of zoom in. Small. Bunch of other stuff. Here's your conversion efficiency, 98% at 60 amps. So you got a 2% power loss. Again, that's acceptable. 1% is awesome. 3% is acceptable. So somewhere in the middle, I'm okay with that, right? And this is all little extras, status display, data logging, blah, 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 you can get. Okay. Other thing is always good is warranty. So this is standard 2-year warranty. You can buy up to a 5-year optional warranty. I actually think that's kind of small. I'd be hoping these things have 10-year warranty, but I guess this manufacturer doesn't want to give a 10-year warranty. Weight wise, this is 12 pounds. So this is actually a pretty small unit if it's only 12 pounds. Okay, so for the maximum power point output or charge control, how we design your solar array. So if you want to get the absolute maximum power, for the battery system, use 60 volts on the battery side and use 60 amps for the current. Now, it's actually outside for the solar array side. For the solar array side, the maximum you can do is 48. So we could change that. Let me be correct in writing. So for the solar side, let's use a 48 volt system at 60 amps. We can number crunch that real quick. So 48 into 60, it's going to be 2.88 watts. Okay. So it's just a little correction on the fly. Nothing wrong with that. 2.88 watts. Okay. So that's how I would, if I'm designing the system, I'll look at a charge controller. I know my limits, and then I could go and look at my solar array, start designing at that size, and see if that's viable as well. Okay. So, yep, that's pretty much charge controllers. All right, to sum everything up. So to charge a battery, you must monitor and control the current and the voltage to limit the battery heat up. Okay, that's what destroys the battery. It's always heat. There are several types of charge controllers you can use. Your very basic trickle chargers and your what's it called? Switch float chargers. Those are like the cheap versions. The 3-stage or 4-stage PWM chargers. These are kind of the more golden standards we should be using in any solar application in today's world. The best type of charger is at least a 4-stage PWM charger, so always should aim for something like this. The size of charge controller, remember you have to derate 156% for margin of error and NEC contention rating. And this reason why is there's a 6 here. If you multiply 125% times 125% is actually 156%. It's not 150. 150 is when you add in them together. But it's very clear in the standard, you don't add the 225% together, you multiply them through. Okay. How is a MPPT optimized for the solar arrays? In a PWM charge controller, user per tube and observe P&O algorithm to find the maximum power point, and just that's a continual operation that runs forever. Okay, as long as the charge controller is online. All right, so that's all I have for today. Thanks for showing up. Basically was a crash course in batteries and charge controllers. And next time we're going to come back and talk about the other side of the solar installation is the inverter, where you're taking your DC system, connecting it to your AC loads in your house and the grid itself. Okay. So thanks for showing up. Hope you guys have a good rest of the day and catch you later.